Howdy, in this video, we'll have a closer look at the structure factor equation. If you recall, the structure factor equation takes this form. So the structure factor is equal to the sum of fj, then e to the power 2 pi I, hx plus ky plus lz. The lowercase fj is the atomic scattering factor. In TEM, the atomic scattering factor is determined by the atomic number. H, K, L are the Miller indices of the diffracted plane to see whether the plane will diffract or not. X, Y, Z are the fractional coordinates of the jth atom in the unit cell. Using the BCC unit cell as an example, the BCC unit cell can be determined by two atoms, one at 0, 0, 0, and the other is at half, half, and half. And they correspond to the X and the Y and the Z's in the structure factor equation. Late last year, my friend, Professor Dalong Zhang, who is a faculty at Baylor University, he randomly asked me why the structure factor equation takes this specific form. Back then, I didn't have an answer for him, and that made me to think more into the structure factor equation. If I break his question down, we can get three sub-questions. The first is why we use the exponential form in this equation. Then why dot product of HKL and XYZ. And lastly, why there's a sum. Let's address these questions one by one. So first, why is the exponential form? The exponential form e to the power of 2 pi I phi can be written down as cos 2 pi phi plus I sine 2 pi phi. This is the general wave equation. And in this equation specifically, phi here is the phase. In the structure factor equation, the phase phi is hx plus ky plus lz. Therefore, the exponential form arises from the mathematics of the wave interference. By the way, the equation you see here is also called the Euler equation. Okay, the second question, why the dot product between HKL and XYZ? Let's imagine now we have an atom and its position in the unit cell is X, Y, and Z. And this happens in the real space. We have the incoming electron beam, which is described as a wave. The phase shift can be expressed as 2 pi g dot r. We'll have a closer look at r and g. R is x, y, and z in the real space. A, B, and C are coordinates in the real space, whereas for H, K, and L, those are the Miller indices of the plane in reciprocal space. And A star, B star, and C star are the coordinate system in the reciprocal space. And this figure, which we have seen previously, depicts the unit cell in the real space and its reciprocal space counterpart. You may have noticed for both R and G, X, Y, and Z, as well as H, K, and L, all these are intrinsic properties of this crystal. There's no information about the incoming electron wave. Then without the information of the incoming wave, how can we get diffraction or interference information? What you are going to see next is something ingenious about the structure factor equation. I will throw out the answer first, then walk you through the other process. The answer is that the wave information is embedded in the G. G can be viewed as a vector of the magnitude of 1 over d. The reason behind it is because if we look at the incoming wave as well as the outgoing wave as two wave vectors, if you do k out minus k in, you get G. If diffraction happens, the scenario has to satisfy the Bragg equation. And in the Bragg equation, n lambda equals to 2d sine theta, wavelength information and the interplanar space information are connected. This is why the wavelength of the incoming wave is already inbuilt in the HKL information. The next thing that bothered me was X, Y, and Z. These are in the real space, whereas HKL, they are in the reciprocal space. How can you do a dot product between the two vectors, one in real space, one in the reciprocal space? In fact, it is possible. Let's look at the crystal in the real space as well as the reciprocal space counterpart example again. Let's look at the atomic position at 1, 1, 1, and we can draw a vector connecting the origin and the point. We also have the 0, 0, 1 plane. To present the plane as a vector, we can do the plane normal. Therefore, this is the plane normal vector. As you can see here, it is possible to project one vector to another vector through the dot product, which is illustrated by the dashed line. The last question is the easiest one to address. Why using the sigma sign or why taking the sum? This is because all atoms in the unit cell, they contribute to the wave scattering. So the linear combination of their effects reflects the overall structure factor. To quickly wrap up what we have discussed in this video, in classical wave mechanics, the phase shift phi can be defined as 2 pi path difference over lambda. In the complex form or exponential form, the phase shift is expressed as g dot r. In this case specifically, because g is correlated with k, the difference between k out and k in, and the k scales with lambda. So that's where we have the lambda information in our phase shift in this expression. And in the exponential form, the phase shift is expressed as e to the power of 2 pi I g dot r. And this is the essence of the structure factor equation. I hope this video gives you a better and a deeper understanding on where the structure factor equation comes from. At the end, I'd like to acknowledge the funding from NSF that enabled our research as well as supported our education effort on the YouTube platform.